Welcome everyone, Physics 100 students, to the lecture for the week of January 3rd. آخر أسبوع وآخر محاضرة semester for the fall semester. We are going to be continuing with chapter 7. So in chapter 7, we started talking about it last time. And you remember that we defined this spooky thing, the potential energy, the energy that we cannot see, which is not in the form of motion. And we learned that when we have potential energy, then we can say that the kinetic energy plus the potential energy, the sum of the two, which is called total mechanical energy, is conserved. ولكن في conservation of energy لو موجود كمحافظة بس. So we started to talk a little bit, and we'll talk more today, about the idea of conservative forces and non-conservative forces. So we're going to see that any force for which we can define a potential energy is a conservative force. And then we're going to see an example of a non-conservative force and how we can deal with a non-conservative force in solving problems. And we'll look at examples of a couple of problems that we'll solve using conservation of energy. And then we're going to look more closely at the relationship between the conservative force and the potential energy. And we're going to see that, in fact, from the potential energy, فكرة قوي جدا لو عرفنا potential energy ممكن هنعدد القوة. We can calculate the force from the potential energy. So the potential energy is the essential information about the system. يعني potential energy معلومات الأساسية على النظام. And then finally, we're going to see that we can apply some of these ideas so that we can sometimes get some insight without having to do a calculation, but by looking at a picture. يعني من صورة energy diagrams. Energy diagrams يعني صورة الطاقة على الcoordinates. الطاقة بتحدد يعني الموقف يتحدد الطاقة. So the energy is determined by the position or by other variables related to the system. So we can plot the energy in a diagram, in a graph, in 3 dimensions or in 2 dimensions. And then there are insights we can get about the system just from those pictures, from those energy diagrams. But before we go into those ideas, I just want to point out something to you which can help you in solving problems. And that is the problem-solving strategies. So in your book, you'll find in many of the chapters في قسم اسمه problem-solving strategy. So this tells you how you can take a systematic step-by-step approach to solve the problems. I urge you, if you're having trouble solving problems, especially في ناس بقول بيفهم كل الفكرة ولكن مش ممكن هيحل المسألة. They can't solve the problems, even though they understand the concepts. Maybe in those cases, it can help to follow these steps. So for every problem-solving strategy, you identify the relevant concepts. So for example, for conservation of total mechanical energy, يمكن هنستخدم conservation of energy ولا يمكن نستخدم قانون نيوتن الثاني. Okay, so the first thing you need to do, you need to decide which one is best. And it gives some hints as to how you decide which approach is the best one to use. So مثلا بالقانون نيوتن في acceleration واكسلريشن عندها علاقة مع الحركة بالوقت. So in other words, since I can get the acceleration from Newton's second law, this is convenient from the kinematic equations to solve for the time. So if the problem involves elapsed time, the energy approach is usually not the best choice because it doesn't involve time directly. On the other hand, if you have a problem where the forces are varying or the motion is along a curved path, يعني الحركة مش على طول خالص، قانون الثاني صعب، لذلك أسهل the طريق conservation of energy. Okay, so then after you identify the concepts, you set up the problem. So مثلا if you decided that you're going to use energy, then you need to identify initial and final states of the system. And then مهم جدا بأي مسألة تعمل صورة. Okay, so you want to draw a picture so that can help you to keep track of all the variables in the problem and all the states in the problem. ومع الصورة تحدد, you need to define a coordinate system. So we've talked about this before. And in the case of conservation of energy, you need to identify which forces are conservative and which are non-conservative. ومع صورة محتاج free body diagram دائما. And then you can list the unknown and known quantities and identify the target variables. Then execute the solution. Execute the solution حاجة سهل جدا، يعني استخدام الفورمولاز. وبعد كده مهم جدا evaluate your answer، يعني نتيجة غريبة ولا مناسبة. So this is a way that you check that you got it working. So here we had the example with problems using total mechanical energy. And in chapter 5, there was similar strategy for problems involving Newton's second law. So if you're having trouble solving problems, بص عليهم، يعني الهدف مش الرد سريع. The target is not to get a very quick answer. The goal is to apply the concepts properly, and then you will get the correct solution most of the time. And notice here it says آخر حاجة the math، يعني قبل كده الطريق محتاج رموز بس. So start solving the problem using symbols. And when you finally get to the point that you have an expression for the target variable, then substitute the numbers. Because if you make a mistake, then if you have the symbols, it's much easier to go back and identify where your mistake was. Okay, so now let's go back to the potential energy and the energy diagrams. So you remember we looked at the example of a mass on a spring. So مثلا هنا في mass on a spring في موقف equilibrium. At the equilibrium point الspring هو مبسوط. يعني this is what's called a stable equilibrium. So مش محتاج أي حركة من موقف هنا. ولكن لو في حركة من نقطة الإيكوليبريم هيكون في potential energy. So anytime I displace the mass from the equilibrium position, if I stretch it or if I compress it, laha potential energy. The spring will get potential energy. So مثلا here we have stretched a distance plus a or compressed a distance minus a. وفي potential energy 1/2 Ka squared. هنا 1/2 Ka squared. هنا 1/2 Ka squared. So in the blue خط الأزرق هو potential energy. Okay, so now when the mass moves back towards this equilibrium position, potential energy بتقلل, it's going down. ولكن total mechanical energy is conserved. It's constant. So the difference goes into kinetic energy, طاقة حركية. And when we reach the equilibrium point, مفيش potential energy. مفيش potential energy, كل الطاقة طاقة حركية. وطاقة حركية يساوي potential energy من موقف الأصل. So the potential energy was just converted into kinetic energy. The total energy is shown here. ما ينفعش الماس هيروح أطول أبعد من A عشان ما فيش طاقة كفاية. The total amount of energy in the system was determined when we stretched the spring and let it go. We put the energy into the spring with the work we did on the force to stretch it. Then we let it go, then the energy is conserved. So the total amount of energy is 1/2 Ka squared, while طاقة كفاية للماس هيروح إلى minus A فقط. مش ممكن أبعد من كده عشان مش طاقة كفاية. Okay, so the conservation of mechanical energy. We said the total mechanical energy of a system is the sum of its kinetic energy and potential energy. So فاكر kinetic energy يساوي work done on the system. شغل على النظام. And potential energy يساوي minus the work done by the force. So لو في كاوة واحدة بس total والكاوة Kawa-Muhafaza, the total mechanical energy of the system is conserved. Okay, so مثلا لو في كوا gravity فقط كل الطاقة is conserved. So we call that conservation of mechanical energy. And we can write it here as an equation. Says that the sum of the kinetic energy and the potential energy min بداية يساوي total mechanical energy min النهاية. And so we can use this in problems. We can do calculations by setting the sum of the initial kinetic and potential energy equal to the sum of the final kinetic and potential energy. So في demonstration على بيرسون اسمه chin basher. في حد بيرفع كرة الفوليبول يعني the volleyball على السلك و هو بينزل وبعد كده بيرفع فين نفس موكب بالواي يعني vertical axis زي البداية, because when you set the height of the ball at the beginning on one side, then you put potential energy into the system, gravitational potential energy, because you lifted the ball. Then if you let it go, it will swing back and forth, but it will never go higher than where it started. So you can be safe if you set it at a level below your chin. You can see this in the video. Okay, so another example with potential energy, high jumper. So the high jumper, he does some work in order to jump. So when he does that, then he gets some kinetic energy. And as he jumps, as he goes higher, some of that kinetic energy gets changed to gravitational potential energy until he comes to the point that, so now by kinematics, نعرف Vx يساوي constant, ولكن Vy بغير عشان acceleration due to gravity, ولكن بالطاقة المعانا the potential energy is increasing, and therefore the kinetic energy associated with the y motion must decrease. Then as he comes back down, the potential energy بيقلل and the kinetic energy will increase, and this will bring him back down. But the sum of the kinetic and the potential energy, once he lifted himself off of the ground, must be the same, must be constant. Okay, so now we said that this conservation of mechanical energy بيشتغل مع كوا-محافظة. So we have two different kinds of forces. We have conservative forces, and the examples we saw were gravity and the spring force. So what are the characteristics of a conservative force? Thacker, we said we defined a potential energy function. We're going to see with this potential energy function, it is a function of the position. of al-mawqif. So the conservative force has a potential energy which we can define as a function of the position. And the conservative force is reversible. Yani irreversible. Yani لو لو في حركة تحت الكوى المحافظة الشغل من الكوى على الفرد يمكن هو هيرجع ولما هيرجع potential energy هيرجع. So if we go along a path, let's say we start in a position and then we go along a path and then we come back to where we started, the potential energy must go back to where it started. The potential energy is a function of the position only. It is independent of the path that I took. So if I go along one path or if I go along another path, if نقطة البداية ونقطة النهاية ما غيروش, then في نفس شغل من الكوى المحافظة. And so the work done will be zero if the starting and the ending points are the same. Now في كوى مش محافظة, مثلا friction. So a force that is not conservative is called a non-conservative force, or في اسم تانية, a dissipative force. So here's an illustration of what we said on the previous slide, that the work done depends only on the endpoints of a path, not the specific path. So مثلا لو في حد هتروح من موقف البداية حتى موقف النهاية بالجبل ولا بالفالي, نفس الشغل. If the beginning point and the end point are the same, then whatever the path in between, the work done by the force is the same. وده حقيقي مع الكوى gravity ولا مع الكوى spring, from the spring force or the elastic force. But the non-conservative forces, we had the example of friction. So friction مثلا when a wheel is rolling on the road, the friction forces GOA. Mechanical energy is lost and converted to internal energy of the tire. This causes the temperature and pressure of a tire to increase. Okay, so some of the energy is going into raising the temperature of the tire. So khalas, that energy is gone. The energy was not conserved. Because of that, the force is not conservative. So we can summarize the conservation of energy in the following way. If we have conservative forces, then the change in the kinetic energy plus the change in the potential energy is zero. When we have non-conservative forces, we have to add the change in internal energy, and this comes from the work done by the non-conservative force. Okay, so let's look at some examples. Okay, so I'm going to look at the following example. هنا من الكتاب. أخوك صغير اسمه بوراي هو بيلعب مع roller skates or roller skates or the skateboard. I don't know what you call it in Arabic, but it looks like this. It has 2 wheels, and then it's just a board. وهو على البداية هو على surface which is vertical, but then it's curves. And the initial height, so هنا أخوك صغير and he is 4 meters above the ground. And now, so what's going to happen? He is going to go down this curved surface. And the surface has a radius of curvature. Oh, sorry. كلام غلط. We don't know h. What we know is the radius of curvature. R يساوي 4 meters. Okay. ولكن لو R يساوي 4 meters, H يساوي 4 meters. تمام؟ اوكي واخوك هو خفيف عشان صغير 30 kilograms. Okay, so now the questions, we're going to have 2 questions here. First, what is V at the bottom of the ramp? Nani his velocity when he reaches the bottom. Okay, so that's the first question. And the second question, when he reaches the bottom, what is the normal force from the ground? So I'll give you a few minutes. I'm just going to pause for a few seconds so that you can pause the video if you choose, and then you can think about how you would go about solving the problem. Okay, so now let's see if you took the right approach to solving it. So one way we could solve it would be that we would, for example, use Newton's second law. Let's think about that. If we use Newton's second law. So with Newton's second law, we could calculate the acceleration. Okay, we calculate the acceleration from the net force. تمام. And then we would add the changes to the velocity, to the initial velocity, of course, was 0. سهلة ولا صعب؟ إيه رأيك? So let's think about it from the point of view of the free body diagram. So let's say now at the top, let's look at the free body diagram at the top. We'll start out like that. So we have your little brother here, and he has his weight, the force due to gravity. But here, there's no normal force. ليه كده? Because his position is vertical. So في mg فقط. But now when he gets to the bottom, let's draw his free body diagram here. So you see he now has the force of gravity on him, and he also has the normal force. الاثنين vertical. So we have mg going like this. And we have the normal force pointing up. Now in between, بين نقطة فوق ونقطة تحت في angle. He's at an angle, right? And the surface is at an angle. So here's the lad, and the force due to gravity is mg. But then we have the normal force will be pointing something like that, depending on the position. يعني اتجاه كوا نورمال بغير بالموقف. ودلوقتي فكر عن موضوع الحركة, the displacement. So هنا the displacement is downward. نفس اتجاه زي الفورس due to gravity. لذلك الشغل يساوي F من gravity times مقدار الدisplacement فقط. بسيط جدا. ولكن هنا يختلف عشان دلتا R زي كده. عندنا مشكلة عشان الشغل يساوي force due to gravity times delta R times cosine theta. وcosine theta وثيتا بغير طول الطريق بغير. هنا تحت dw يساوي 0. لكده عشان الحركة على اتجاه horizontal. يعني عمود من الكوى. So صعب الكنونوتا. لذلك هنستخدم conservation of energy. من conservation of energy في potential energy هنا حركة طاقة حركية زيرو، وتحت في طاقة حركية فقط، وطاقة حركية فيها velocity. So we can say the initial kinetic energy plus the initial potential energy. Potential energy here is due to gravity. يساوي the final kinetic energy plus the final potential energy. Initial kinetic energy يساوي 0. Initial potential energy mgh. Final kinetic energy 1/2 mv squared. And final potential energy يساوي 0. لذلك B يساوي square root of 2gh. والله نفس نتيجة زي free fall. تمام؟ هنا زي free fall. ليه كده؟ كان في كوا gravity. It did work. ولكن الشغل من normal force يساوي 0. يساوي 0 عشان دائما الحركة عمود من normal force. Therefore the dot product n normal force dot dr يساوي 0. Okay, so now in this case we had the square root of two times 9.8 meters per second squared and then multiplied by 4 meters. And so notice we have meters squared per second squared. And when we take the square root, we get meters per second. And this is equal to 4 times 9.8, square root of 78.4, which is 8.85 meters per second. Okay? So that's the answer to part A. What about part B? What is the normal force at the bottom of the ramp? Okay, how will we solve this? Now we can use Newton's second law. Okay, so we take our free body diagram. So our free body diagram at the bottom looks like this. So we can write Newton's second law here. So the sum of the forces on your brother is equal to his mass times his acceleration. And we'll start out with the forces in the y direction. Okay, so now in the y direction, we have the normal force pointing up. We have the weight pointing down, and this must be equal to the mass times the acceleration. Now, what's the acceleration here? So we have uh, we are going in a circle, okay? So we have two kinds of acceleration. Eine, radial acceleration. Radial acceleration points up. Eine tangential acceleration. But the component of the acceleration in the y direction so this actually is I should write it. Sorry. I should write the acceleration here as a sub y, okay? Which is the radial acceleration. And the radial acceleration, you'll remember, is v squared over r. So we have mv squared over r. Okay, so we can say normal force is equal to mg plus mv squared over r. And then when we substitute in the numbers, actually, we saw that mv squared is equal to 2mgh. So this is actually mg plus 2mg over r. Okay, and which is equal to just 3 times mg. So this turns out to be 30 kilograms times 3. So we can say it's 90 kilograms times 9.8 meters per second squared. and that is equal to 882 newtons. Tamam? Okay, so we solved the problem. We solved the problem using conservation of energy. Uh, Now that was possible because energy was conserved. Energy was conserved because the normal force did no work. All work was done by gravity. Which is a conservative force. Okay, but now what? What if there is friction? That is, what if there's a non-conservative force, like friction? And V at the bottom is equal to 7 meters per second. Then I want to ask, what was the work done by friction? So again, I'll give you a few seconds if you want to pause the video and work it out for yourself before we start on it. Okay, faddal. We can use the conservation of energy, but taking into account that the total energy is not conserved because work is being done by friction. So we can write the equation like this. We take the initial kinetic energy plus the initial potential energy, and then if energy was conserved, then we would set that equal to the final kinetic energy plus the final potential energy. But we know that work was done by friction. So the energy is changed by an amount equal to the work done on the object by friction. So this will be, we'll call it W sub F. Work done by friction. Work done by the non-conservative force. Okay, so now what we need to solve for is this WF. So WF should be equal to the final kinetic energy minus the initial kinetic energy, or the change in kinetic energy, plus the final potential energy minus the initial potential energy, or the change in potential energy. Okay, so now the final kinetic energy is 1/2 mv squared. And the initial kinetic energy is 0. And the final potential energy is 0. And the initial potential energy is mgh. Okay, so the work done by friction will be the final kinetic energy, which is 1/2 times 30 kilograms times 7 meters per second squared And then we have minus mgh, which is minus 30 kilograms. Times 9.8 meters per second squared. And actually, we already calculated that before. And then we have 4 meters as the initial height. Okay, so if you substitute all that in, we get, or at least this is my calculation, minus 441 Newton meters. So let's check our units. We have kilograms, meters squared per second squared. So remember, a Newton is a kilogram meter per second squared. So this is a Newton meter or a joule. A joule or a Newton meter is the unit for energy. Okay, so notice هو negative. ليه كده؟ عشان الفريكشن اتجاه الفريكشن عكس من اتجاه الحركة. So the friction was always in opposing the motion or opposing any change in the motion. So the friction was like that. So the friction did negative work. And as a consequence, our velocity أقلل من النتيجة من غير friction. So without friction, we had 8.85 meters per second. With friction, we had 7 meters per second. Okay? I'm going to stop the video now, and then I'll resume with a different video for the second part of the lecture. We'll look at another example problem, and then we're going to briefly define the power, and then we're going to look at the relationship between the potential energy and the force. Assalamu alaikum.